How we used log tables. Hello. When I teach logarithms to A-level pupils, I sometimes talk about how we used to use log tables for doing calculating when I was at school, before calculators were widespread, using a book like this. And they're often fascinated. So I thought I would make a video about it. So I shall talk about how log tables were actually used, and then talk a little bit about how the common logarithms, that is logs to base 10, are still a bit relevant to today's education, for the benefit of today's pupils and also for younger teachers who may not have met these ideas before, because it's not just of historical interest, there's some interesting mathematics here. So let me share my screen. So I'm assuming you are more or less familiar with the view of logarithms that we teach in schools nowadays, and that is to say that the log function is the inverse of this exponential function, 10 to the power of something or other. So if we're using function machines, for example, y is log to base 10 of x if x is 10 to the y. Or in graphical terms, this is the graph of y equals 10 to the x. This is the graph of y equals log to base 10x, and they're reflections of one another in this line. And if we take that approach, then these are the rules we can deduce about how logs work based on the power laws. So log to base 10 of a times b is log to base 10 of a plus log to base 10 of b. And similarly, log to base 10 of a divided by b is log to base 10 of a minus log to base 10 of b. And we can do powers and roots in the same sort of way. So if we turn that around a bit, we can say that a times b is 10 to the power of log to base 10 of a plus log to base 10 of b. And that provides us with a way of multiplying. So why would anybody want to do that? It looks quite complicated. Well, let me explain why you'd want to do that. So supposing you wanted to multiply these two numbers together and you didn't have a calculator, you've just got pencil and paper, and you want to work it out to 4 figures of accuracy, let's say. So what you do is something like this, wouldn't you? You do log division, log multiplication, let's say. So what is this? You've got 23 digits to work out? Well, actually, you don't need these ones here, do you? If you're only working to 4-figure accuracy. But it's still about 20 digits you've got to work out without making a mistake. Whereas if you could look up the logarithms of these things easily and unlog the answer, well, the logarithms of these two, then you've only got to work out 5 digits without making mistakes, and then anti-log the answer. That's to be a very good buy if you could do it. And so let's see how that actually worked. Well, before doing that, it's worth saying, though, that this model of logarithms was absolutely not what the people who invented logarithms had in mind, John Napier and Henry Briggs. And that's because this function 10 to the x didn't see the light of day for another 100 years or so. So how they invented logarithms without having access to that idea is one of the triumphs of human ingenuity. But that's a story for another day. But the legacy of that story is that this 10 to the x function is not called 10 to the x function in the context of 4-figure tables. It's called the anti-log function. So a times b is the anti-log of log a plus log b. And we drop the 10 from now on because logs are always common logs. They're always to base 10. A divided by b is anti-log of log a minus log b. A to the power r is anti-log of log a times r. And the r through to a is the anti-log of log a divided by r. Okay, so let's see how this really works. So here's the log table. This is it. This is the whole log table. It's a single page opening. It has the logs of every number to 4-figure accuracy. So let's see how that works by looking up the log of 6.543. Now 6 and a bit is between 1 and 10. So its logarithm is between 0 and 1. And what we do is we look up these digits in this table. The first two down this column, there's the 65. Then we put our ruler across here. We look the third digit up here, and that gets this number. So that tells us that the log of 6.54 is 0.8156. And then what we do is we interpolate linearly between here and here. Well, of course, the log is not a linear function, but it jolly nearly is if you zoom in closely enough. So if you look along this line, for example, and look at the difference, well, what is that? It's 7, 6, 7, 7, 6, 7, and so on. So it's very nearly linear. And that allows us to interpolate linearly. And the tables provide a shorthand way of doing that. These are called proportional parts. What we're looking for is 3/10, or we're looking up a 3 here. We're looking 3/10 of this distance from here to here, and that's, well, this table tells us is 2. So that tells us that log of 6.543 is 0.8158. Now, the beauty of using logs to base 10, of course, is that we can look up any number this way. So, for example, log of 65.43 is 1.8153 because it's 65.343 is 10 times that, so its logarithm is 1 more. Similarly, log of 654.3 is 2.8158. And if we're using scientific notation, log of 6.543 times 10 to the 7 is 7.8158. Okay. So there's some terminology we ought to learn here. So this piece here of a logarithm is called the characteristic, and this piece is called the mantissa. And so to work out a logarithm, you look up, you take the significant digits and look them up in the table to give you the mantissa, and you calculate the characteristic by looking where the decimal place is or looking at this number. Okay, we do the other part as well. So looking up log of 1.234, there's a slight subtlety here that at this end of the table, these proportional parts are much bigger, and actually the differences are not quite linear. I mean, there is a difference here. So this is 36 here, it's only 34 at that end. So there are ways of dealing with that if you really want to be precise about the fourth digit, but frankly at school we never bothered about that. So we just ignored that problem. And log of 1.234 is 0.913. Okay, and then when you've added the two logs, you have to look up the answer in the anti-log table. And as you'd expect, this is pretty much exactly the same process. So we zoom in a bit on the bit we need. Anti-log of 0.9071. So we look up the 90 here, and the 7 is here. So that tells us that anti-log of 0.907 is 8.072, and then we want 1 in this fourth place. The proportional part gives us 2, so anti-log is anti-log of 0.9071 is 8.074. Okay, and similarly, of course, if anti-log of 1.9071 is 10 times bigger, so it's that, and anti-log of 7.9071 is 8.074 times 10 to the 7. Okay, now there's a subtlety about negative numbers, or say numbers whose logarithm is negative. Normally, consider this number on the number line. We normally refer to that by measuring backwards from -1 and calling it -1.3. Well, we could measure it the other way from -2. And when we do that, we refer to this as bar 2.7. So that's 0.7 beyond to the right of -2. And that bar notation was universally used for logarithms. And the reason for that is that, as you shall see when we do some examples, it's really no more difficult to add and subtract numbers with the bars in them than the ordinary numbers, but it's much easier to look them up. So if we go back to this table here, we've seen these things here. Let's take the next one. So log of 0.6543 is 1 less than that. Well, we can read that straight from the table because that's just bar 1.8158. So that's much easier to work that out rather than calculating negative 0.1842. And similarly, log of 0.06543 is bar 2.8158. And the scientific notation one is nice because 6.543 times 10 to the minus 7 is bar 7.8158. Okay, so that's the process that's the notation that was always used for negative numbers in logs. Okay, so now let's have some look at some real examples. So I've taken examples from this particular paper, an O-level paper in 1964, which is actually a year after I took my O-level. Nowadays, we fret ourselves and worry ourselves about what the purpose of a mathematical education is and what we should teach and so on. Up till about 1964, one purpose of a mathematical education was abundantly clear, which is to train people to be able to calculate quickly and accurately. Because a lot of jobs depended on people being able to calculate quickly and accurately with a pencil and paper or with log tables. And so the O-level was a qualification which showed that you could do that, apart from anything else. So let's look at some questions. This question is a sort of starter question, which explicitly asks you to use tables to make some calculations. So let's start with this one. So what are we going to do? We've got to multiply that by that and divide by that. Well, so we're going to take logs. So we take log of that, that's at a bar 1 number, and it turns out to be that, and that's a 1 point something or other number, so it's that, and that's another bar 1 number. So we add them, we get 1, 8, 0 carry 1, 1 carry 1. Now bar 1 plus 1 is 0, plus the carried 1 is 1 again. And then we subtract this. So that's 8 carry 1, 8 carry 1, 3 carry 1, 2 carry 1. So 1 minus bar 1 is 2, minus the carried 1 is 1. And then we anti-log that, and we get 17.31. Okay, so that's how you use logs in a simple example. It's not just logs, though. So the tables also have trigonometric functions in. So let's look at one of those. So here's a table of natural cosines. I'll explain what natural means in a minute. It's just cosines. So it's much the same. You see, you've got degrees in the left-hand column, and then you've got six minutes across the top and single minutes in the proportional parts. So it's exactly the same process, looking at trigonometric functions. So going back to this example, what are we going to do? We take 1, we look up the cos of 84 degrees and 23 minutes, and we subtract them. And then we have to take the square root. Now, you might think what we have to do is take the log of this and halve it and then anti-log it. But actually, square rooting is such a common operation that the table's provided a specific table for doing that. So the square root table in the book. This is actually slightly subtler than the others. So there are sort of two answers. So, for example, the square root of 9 is 3, whereas the square root of 90 is 9.4 something or other. Square root of 900 is 30. So you have to use your nous a bit with knowledge of where the decimal point is to work out which of these two values you need to use. And then you need to place the decimal point in your answer. So in this case, it's not very difficult. So square root of that is going to be that. Okay, now this is a bit of an exceptional use of a trigonometric function, because very often, as soon as you've got a trig value, the first thing you're going to do with it is multiply it by something such as a length. And that would mean taking logs again. So in fact, there's a shorthand, a shortcut. There are also log sign tables, and that's what the natural sign means. And natural signs are just signs as opposed to log signs. So this table gives you the log of the sine of an angle, and it's exactly the same, you see. The degrees here, 6 minutes and single minutes. So let's see an example of that being used from that same paper. So we're asked to find the area of this little triangle. So the calculation we want to do is a half times 2 times 1.6 times sine 64. Well, we can do the half times 2 straight away. So it's 1.6 times sine 64. So we need to look up the log of 1.6. That's a 0 point number. Sine of 64 is a bar 1. And that's that. We add them, and then we anti-log them, the answer to get the area of the triangle. Okay, there's a slightly more substantial question from the end of the paper. I'll just let you have a look at that. Okay, so what are we being asked to do? The amount of money we have to recover each year is 4.38 times 10 to the 8 pounds times 5%. And we do that over 365 days, 120 trains each way. That was a bit of a trap, wasn't it? Times 250 tons. So that gives you pounds per ton. So numerator, you multiply all these two numbers together. Log of that is an 8 point number. That's bar 2 point something or other. Add those up. And then you calculate the denominator. That's a 2 point number, log 2 is that, and log 250 is that. You add those up. And then you would expect to subtract that number from that number and anti-log the answer. Actually, on this occasion, you see these numbers are within the accuracy that we're working the same. And so the difference is 0. So the answer is 1. So it's £1. Actually, if you work this out exactly, it is exactly 1. The numbers all cancel. That's quite fun. Right. Let's have a look at the rest of the table of the book, table of contents of the book. We've got logs and anti-logs. We've got the log trigs and the natural trigs. Square roots we've seen. It's also got a table of squares and reciprocals, Napierian logs and hyperbolics and what have you, and a few other bits and pieces. Okay, now what it doesn't have is the inverse tables like the anti-logs for the trigonometric things. So you have to use the tables backwards to do that. So let's see an example of that. Supposing you wanted to work out arctan of 0.2. Well, you've got to find 0.2 in the table, haven't you? So it's somewhere in here. So it's going to be 11 degrees and something. And we want to move 2 along from here to here. So in other words, we want to find a 2 in the proportional parts. Well, there isn't a 2, there's a 3, that'll do. So that's 1 degree beyond, 1 minute beyond 18 minutes. So the arctan that we're looking for is 11 degrees and 19 minutes. Okay, and we're the same with the log trig functions. There isn't a question on the paper that uses any of this, but I've made one up. So here's a simple question using the sine rule. What's this angle? So this is the calculation we're trying to make, is it? Sine of x is sine of 62 times 11.4 over 16.7. Okay, so what are we going to do? We work out log sine of 62 degrees, it's that. Log of 11.4 is that. And we're going to add those and then subtract log of 16.4, and we get this. And then we look this up in the log sine table used backwards to get that. Okay. Not the least interesting page in this book is this one. You'll see that the book is first published in 1913 and was reprinted every year or every other year, right the way through to 1973 when this particular edition was printed. I don't know how many more there were after that, but probably not many, because by the late 70s, calculators were pretty widespread, and I think the bottom had fallen out of the market for four-figure tables. I'd love to know what these corrections were in 1962 and 1965. My guess is that that's when they first used a proper computer to check all the numbers and found there was a mistake, but I don't know. Okay, now I don't suppose anybody and professionals, if you like, in what we now call STEM careers, really use four-figure tables very much, because they could use a slide rule, which is a sort of mechanical version of log tables. I'm not going to explain how those work. I'm sure there are plenty of other videos about that. And you can get 3 figures of accuracy out of that if you're careful. If you wanted more than that, you probably went to the other standard, which was 7-figure log tables, using a book like this. And you'll see that this is actually quite a substantial book. And it allows you to work to 7-figure accuracy. And let's just see how that works. So it's probably similar. The first 4 digits you look up and down the left column, the 5th one along here, and then you do the 6th and 7th with proportional parts. In fact, I mean, the log function is so nearly linear when you've zoomed in this far that all the differences across both these pages are either 58 or 59, and this gives you the proportional parts. But let's see how that actually works. So let's look up log of 7.474747, just for fun. So you look up the first 4 digits in the first column, having found the right page, of course. So that tells you that for all these numbers around here start 873, and then the following 4 figures are in the table. So then we go to 747, that gives us this one. So log of 7.4747 is 0.8735938. And now we look at this difference and we find that it's 58. Sometimes you'll have to look on the neighboring page to get the right proportional parts, but this time we're on the right page. This is 58. So we're looking for 48 hundredths of 58. So the way this proportional part tables work is that the 6th digit, this is the 6th digit, and we want 23. So 23 is 40 hundredths of 58. And the 7th digit is 4.1. So 4.1 is 7 hundredths of 58. So 7.47, log of 7.4747, we add the 23, and then for the 7th digit, we add another 4. Okay. Now, there aren't any anti-log tables in this book, so we have to use this table backwards, which is a bit more tricky, but I'll show you how that works. And I'll do a simple example which illustrates something else. So I'm going to find the cube root of a half using 7-figure log tables. So we look up log of a half first, and it's that, bar 1 point something. Now, we've seen that adding and subtracting bar numbers is really no more difficult than in the standard notation. Now, that's not true if you're going to do multiplication and division. And so there was a trick that we always use. So we've got to divide this number by 3, haven't we? So what we actually do is add 3 to it to make it positive, then divide by 3, and then subtract 1. And I'm interested to see that the nice thing about this book of log tables that I've just recently bought is that it's got quite an extensive section in the beginning about how to use them, and it includes this trick which we were taught at school. So let's do that. So we add 3, we divide by 3, and then we subtract 1. And then we have to look this up well, we would look it up in the anti-log table if there were such a thing. We've got to find anti-log of bar 1.89965667. So we're going to find that in the log table. We find the 899 easily enough. So we're somewhere in this block. Then we're looking for 6567 in this block. So that's somewhere around here, look. So it's between here and here. And in fact, it's 3 beyond this one, isn't it? Even 1 in the 6th place is too much. That would take us 6 beyond 6,4. So we want to move 3 beyond, which is going to be 5, isn't it? This 5 here. So anti-log of bar 1.899657 is 0.7937005. So we do the anti-log, and that's the answer. Okay, so that's logarithms as we actually use them. I confess I never actually used 7-figure log tables in earnest. So by the time I was in the workplace needing to make proper calculations, I got a calculator. Okay, but I think log space 10 still have some interest. To say that they're useful might be a slight exaggeration, although I do use them. That's based on a table of 1-figure antilogs. So antilog of 0 is 1, and antilog of 1 is 10, of course. The rest is based on the rather remarkable coincidence that log 2 is almost exactly 0.3, and so log of 2 is 0.3. Okay, so log of 4, which is the square of 2, is 0.6. Log of 8 is 0.9. Log of 16 would be 1.2, so log of 1.6 is 0.2. And then we get 3.2 and 6.4. And we go the other way, halving. So log of 10 is 1. So log of 5 is 0.7. And anti-log of 0.4 is 2.5. And then you end up with 1.25. And if you did it one more time, you'd get 6.2. So it's 6.3. It doesn't really matter. We only want this very approximately. So we can work out logs and anti-logs using this table. To look out a log, you just look for the nearest one of these to whatever number you're looking at. Okay, now there are several uses for this table, one of which is just to do with giving a good handle on what exponential growth is like. So these numbers here, I've plotted them. So these numbers here are along the y-axis, and they give you a nice feeling for exponential growth, just going through these numbers mentally and seeing what exponential growth looks like. I particularly like this one, actually. So a 25% increase is 1/10 of the way towards a 10-fold increase. So 10th root of 10 is 1 1/4. Interestingly, a bell, so a bell is a measure of power, and it's a 10-fold increase, and a decibel is a more common measure of power, and that's a 1/10 of a bell, so it's on the log scale, so it's a 25% increase. That's quite interesting, but generally the notion that a 25% increase is 10% of the way to a 10-fold increase is quite a good way of getting grasp of exponential growth, and a lot of these other ones fit in very nicely into a mental model of what exponential growth is like. A square root of 10 is 3.2, for example. That's halfway there. And it doesn't matter, of course, which exponential growth we're talking about. So here's a different one. It's exactly the same picture. Now, the other use we can make for this is sort of mental Fermi estimating. If you do Fermi estimating in your head, you can do order of magnitude easily enough, but that's very broad brush. And if you're doing any number of multiplications, you can well be an order of magnitude out. So that's not very good. You can work to one figure accuracy, one figure of logarithm accuracy really quite easily. This table is quite memorable. If you run through it a few times, you can sort of get the picture and remember it. And you've got this 1, 2, 4, 8, 16, 32 business going on, which can help you to remember it. So let's just use that to do a Fermi estimate. I've always thought population density is measured the wrong way up. You get people per square mile or per square kilometer. I always think area per person is a more intuitive measure. So let's work that out as a Fermi estimate for the whole world. How many hectares does everybody in the world have? We shared it out equally. Well, what do we know? What I happen to know is the circumference of the Earth is about 40,000 kilometers. Trivia fact, it used to be exactly 40,000 kilometers because a kilometer was once defined to be a 10,000th of the way from the North Pole to the equator through Paris. Be that as it may, it's approximately 40,000 kilometers nowadays. And that is, so the log of 40,000 is 4.6. 4 is 6. So I don't know really what the right way to notate this. I'm calling it log kilometers. So we can work out the radius by dividing by 2 pi, which is approximately 6. So that's about 0.8. So we subtract 0.8 and we get 3.8 log kilometers. We square it, doubling the log, get 7.6 log kilometers squared. Now we multiply by 4 pi, which is about 1.25, isn't it? So about 12.5 rather. So that's about 1.1. So that's 8.7 log kilometers squared. Okay, now about 30% of the land area, of the area of the Earth is land, I believe. So that's about half. A log of that's about half. So 8.2 log kilometers squared land area of the world. The population of the world, I believe, is about 7.5 billion, is it? Something like that. Well, that's 9.9 log people. Subtract the number of log people from the number of log kilometers squared, you get bar 2.3. Well, that's kilometers squared per person. Hectares per person is probably more intuitive. That's multiplied by 100. That's 0.2 log hectares per person, and that, of course, is 2 hectares per person. And that's actually quite accurate. So, and you can, if you can remember this table, you can do that. So, as I say, I'm not claiming it's actually useful, but it's quite fun. Okay, let's do it again for UK. It's quite interesting, actually. So what do we know about the UK? Well, I happen to know that it's 800 odd miles if you cycle from Land's End to John O'Groats. Well, that'll be a huge overestimate of the north-south crowfly distance. Let's call it 1,000 kilometers. So that's 3 log kilometers. The width is quite tricky, isn't it? It's sort of trapezium shaped. It's much narrower at the top and the bottom, but let's call it 250 kilometers. That's 2.4 log kilometers that way. So the area is 5.4 log kilometers squared. The population is 65 million. That's approximately 7.8 log people. There we are, that's that row. Subtracting that from that, we get bar 3.6 log kilometers squared. Turning to hectares, it's bar 1.6, which is 0.4 hectares per person. Again, that's actually surprisingly accurate, given the rather hand-waving approximations I've been making. It's surprising that it's not more than that, actually. It's only 5 times the density of the world at large, or a fifth of the area per person. That's quite surprising, given that the whole world includes, well, Antarctica and Canada and Central Australia and the Sahara Desert and Siberia and all those enormous places where essentially nobody lives at all. Anyway, those answers are fairly accurate. It's quite interesting. So there you go. Logs as they were actually used, and logs as they might be used, or at least be enjoyed in today's world. Thank you for listening.